So I'm going to show you an animation and then do some chemistry as well. Okay?
Oxygen is picked up in the lungs and transported to the other body tissues in two ways: attached to hemoglobin molecules in red blood cells and as a dissolved gas. Oxygen is not very soluble in water. Because of this, only a very small percent of the oxygen is transported as a dissolved gas.
And frankly, we're going to ignore that. Even though there is some just floating around, 1.5%, I don't care, you don't care, we're going to skip that. We're going to focus on the oxygen that's not just floating around. It's in the RBCs, which you learned last term, right? RBCs carry oxygen. Okay? So now we're going to see the oxygen part of this. So we're going to look at the blood part.
Almost all oxygen is transported bound to hemoglobin molecules located in red blood cells. Hemoglobin molecules consist of 4 polypeptide chains. Each polypeptide chain contains an iron-bearing heme group. An oxygen molecule binds to each iron ion located in each heme group. Hemoglobin that is not bound to oxygen is called deoxyhemoglobin. Loading or association of oxygen to deoxyhemoglobin forms oxyhemoglobin.
All right, so we'll be using those terms, but just review from last term, right? We taught you hemoglobin, the iron-bearing hemoglobin. We looked at it from a blood point of view. This is the oxygen point of view. So you have 4 oxygen molecules being carried on the RBCs. Okay, so now we're going to do the next picture. What am I supposed to do? Click on the RBC. Okay, fine. Now comes the chemistry part.
The production of oxyhemoglobin can be illustrated through the following reaction. Oxygen binds with deoxyhemoglobin to form oxyhemoglobin and hydrogen ions. This equation represents the binding of oxygen to the iron ions in heme groups in hemoglobin molecules. Oxygen association occurs at the lungs.
All right, so let's start writing those equations down. You're going to have 4 sets of equations, about half a page each, so plan ahead. So here we go. I'm going to do the oxygen equations over here. Now later I'll do other equations over there. So right now, I'm at the lung, at my alveoli. That's the equation you just saw on the screen. So I'm going to write it slightly differently. Okay? Now we'll figure out what I'm writing. Okay, so I'm writing HB plus O2, arrow HbO2 at the lung. So someone help me out. What's HB stand for? Hemoglobin. It's on the RBC you learned last term. O2 stands for? Good, you got that far. Arrow means magic. HbO2 means what? Oxyhemoglobin. And tell me why you said oxyhemoglobin. Because it's oxygenated. So what kind of hemoglobin was this one over here if it doesn't have oxygen? Deoxyhemoglobin. So I have deoxyhemoglobin, grabbing oxygen, magic happens, becomes oxyhemoglobin. I'm ignoring the H, that's not really critical for this class. So I'm not going to use the H thing. I'm just going to do those. All right? And this is at the lung. So let's figure out where these came from. The HB is in my blood. Where's the oxygen come from? From the alveoli, from my air sacs. So the air comes in, diffusion makes it go into my blood, and then it binds to the hemoglobin to become oxyhemoglobin. Does that make sense? What you saw? Okay, we have a word for this, which we'll keep going. There's some wording to describe that, which is right here. Loading. You've just loaded the blood. So this is called the loading equation. Loading. So I'm loading my blood. What am I loading it with? Oxygen. So that's called the loading equation or the association equation. Right. Some people say association, some say loading, I say loading. That's fine. So this is the loading or association equation of oxygen in my blood at my lungs, right here. That make sense? Okay, let's keep going, because there's more. Click on the tissue cell. So,
The dissociation of oxygen from oxyhemoglobin can be illustrated through the following reaction. Hydrogen ions bind to oxyhemoglobin to form deoxyhemoglobin and oxygen. This equation represents the unbinding of oxygen from the iron ions in heme groups in hemoglobin molecules. Oxygen dissociation occurs at the tissue cells.
all right. So now we're going to go to my tissues. My other column here is my tissue cells. Where are those at again?
Everywhere.
Anywhere I want. All right. So now I'm going to write an equation that represents what I'm doing at my tissue cells. There's my equation. HbO2 arrow O2 plus Hb. Can anyone look at the two equations and tell me a relationship you see? They're opposites. I wrote them intentionally as opposites to let you know that they're just reversing. So if you remember one, you flip it around and you get the other one. These are chemically the same, right? Just opposite direction. So we have oxyhemoglobin. Magic happens. I make oxygen plus deoxyhemoglobin. What am I going to do with that oxygen that's sitting out there? It's going to go to my tissues. I'm going to send it to my tissues. Because I let it go from the blood, now it's free. How could I describe that? It's not loading anymore. What's it doing?
Unloading.
It's unloading. Can't do the G anymore. So I learned it as the unloading equation, which is perfectly good. You load and unload. If you prefer a bigger doctor word, you say it's dissociating. These are fine. Either way is fine. I like loading and unloading. So I load up my lungs, I unload up my tissues. Yes?
So the hydrogen is pushing the oxygen off.
Basically, yeah.
So that's why acidosis is bad.
Yes.
Okay.
And we'll learn that next week when we do Haldane effect. So as the acid levels change, it affects this in the CO2. So do okay on my loading and unloading of oxygen. So I pick it up in my lungs, I dump it at my tissues with hemoglobin. Make sense? Okay, that was the easy one. Now comes the hard one. Leave some space. We're going to do the exact same thoughts. Just the board. We're going to have lung and tissue. But this time we're doing the carbon dioxide, not the oxygen. So those are the oxygen steps. Over here are going to be the carbon dioxide steps. There's more of them. So now we're going to do the carbon dioxide transportation. All right?
Carbon dioxide is picked up at the tissues and carried in the blood to the lungs for disposal in three forms: as bicarbonate ions, as carbon dioxide bound to hemoglobin, and as a dissolved gas. A very small percent of carbon dioxide is transported in the plasma as a dissolved gas.
So about less than 10%. So this is our first one, where there's three ways we're going to transport it, which they mentioned. But this little one says as a dissolved gas. We're going to put that as number one at our tissue. Why am I putting it on the tissue side? Why is it over here? That's where CO2 comes from, right? CO2 leaves my tissues and goes in the blood. So the CO2 can stay in the blood as a gas. Do you know anything you may have drank today that has CO2 as gas bubbles in it? Soda pop, right? That's what this is. CO2 is a bubble in your blood. So CO2 can enter my blood as a gas and just stay that way. That's less than 10% of your CO2. Okay? Let's keep going. So that's one way we get CO2 just bubbling in your blood. Think of soda pop. Okay? That's the easy one. There we go.
A slightly larger percent of the carbon dioxide is transported bound to hemoglobin as carbaminohemoglobin. Carbaminohemoglobin is formed near metabolically active cells and carries carbon dioxide from systemic cells to the lungs. When the blood reaches the lungs, carbon dioxide dissociates from the hemoglobin and diffuses out of the plasma into the alveolar airspace.
Okay. I'm going to play this one more time. I want to show you something, okay?
A slightly larger percent of the carbon dioxide is transported bound to hemoglobin
Watch up
as
here.
carbaminohemoglobin.
Okay, look at the oxygen on the hemoglobin. And then look at the carbon dioxide on the hemoglobin. Are they in the same spot? No. So that's an important idea, is that the oxygen is one place in your hemoglobin, the CO2 is a different place. They're not competitive, right? So that's why your hemoglobin can still carry oxygen fine, as well as carrying CO2. They're not competing for the same heme group, right? So that's why they changed the name. So let's write that one as number 2. So step number 2, we look at the, I'll play it one more time. There's an equation that appeared right here. So we're going to write that equation down. How about walking all the way over the room?
Carbaminohemoglobin is formed.
Boom, that one. That's our level 2. So you can take CO2 plus HB. What was HB again? Hemoglobin. Magic happens. What do you notice the difference between how I wrote that HB something and how I wrote this HB something? Very good. Notice this oxygen is connected to the hemoglobin. They're together, they're bound. CO2 is not bound to the hemoglobin in the same sense. That's why we put the dash. Okay, what do you call that thing there? Carbaminohemoglobin. Carbaminohemoglobin. I wish there's an abbreviation, there isn't. So carbaminohemoglobin. Blah, 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 blah. That's carbamino because it has a carboamino group on the hemoglobin. That's carbaminohemoglobin. All right, so some CO stays as bubbles. Some goes to your hemoglobin and sticks like that. All right? Let's keep going.
Near metabolically active cells and carries carbon dioxide from systemic cells to the lungs. When the blood reaches the lungs, carbon dioxide dissociates from the hemoglobin and diffuses out of the plasma into the alveolar airspace.
Perfect. Let's do that over here. So now we got to figure out what we're going to do with the lungs for these ones. We have the same 3 steps. Okay, the first one, when the CO2 stays as a blood gas, what do you think happens when it gets to the lungs? It can or it can come out. So the CO2 bubbles out. So it bubbles into your blood and it bubbles out of your blood into your lungs. Okay? What do you think I'm going to do on the second equation to that carbaminohemoglobin? Reverse it, like I taught you. So I'm going to do HB-CO2, magic happens, HB plus CO2. I'm going to reverse the equation like I taught you. And then this CO2 is now free to go out to your lungs. I'm unbinding it, if you want to use that word. Right? So I pick it up at my tissues, I dump it at my lungs. Right? So far so good? The third one is where you're going to hate me. We got to do the third round, which is the predominant way you travel CO2. Here we go. The most important transport mechanism is the longest one. I'm just the messenger.
Most of the carbon dioxide is carried in the form of bicarbonate ions in the plasma. The carbon dioxide in the plasma diffuses into the red blood cell. There it undergoes a chemical reaction catalyzed by the enzyme carbonic anhydrase and is rapidly converted to bicarbonate ions. As levels of carbon dioxide increase, the production of bicarbonate ions increases.
Okay, here we go. We're going to write all that out. So, step number 3, CO2 plus H2O makes H2CO3, which makes H plus HCO3 minus. Start writing now. That's the third and most common way you transport CO2. The CO2 binds with water, making these things, H2CO3, H and HCO3 minus. So come on, chemistry majors, help me out. H2CO3 is carbonic acid. I knew that, sure. H plus is hydrogen ion. HCO3 minus is bicarbonate ion. That's why you didn't take Biology 112 before you took this class. All right? So I'm going to make carbonic acid. It's going to be associated to two ions, H's and bicarbonates. Where does this occur? So where is that happening from that video? In the RBC. So this whole equation, all the steps is in the RBC, within the red blood cell. Not the heme, but actually within the red blood cell, where the plasma is. Now, there's one other thing. There was an enzyme, right? Did anyone catch the name of that enzyme? How do I know that's an enzyme? ACE, right? Carbonic anhydrase. If you look at where it is, it's on that arrow right there. So we're going to add that. So this arrow is the CA enzyme. CA is carbonic anhydrase. ACE means enzyme, anhyd means without water. Carbon is what it's based upon. So on my red blood cells, I'm going to take carbonic anhydrase to convert CO2 plus H2O into an acid and some ions at my RBC in my blood. So far, so good? Okay, let's keep going. You're half done. Because now we got to get that to my lungs. So here we go.
The bicarbonate ion diffuses into the plasma, where it is carried to the lungs. In order to maintain electrical balance in the red blood cell, the movement of the negatively charged bicarbonate ions out of the cell is balanced with the movement of negatively charged chloride ions into the cell. This process is called the chloride shift.
Yeah!
Carbon dioxide is generated near the alveoli. The carbon dioxide that is produced diffuses into the alveolus for removal from the body.
Ooh, no. Ooh. Let's go back to that little bit of the chloride shift, and then we'll go through this part. So, when I do all this equation, which thing came out of the red blood cell? The bicarbonate leaves the RBC. Leaves. And what has to go in to replace it? Chloride, chlorine. Saladin spends 2 paragraphs talking about the chloride shift. That's what he means. As this negative ion leaves, you have to add a negative ion to make it stay neutral. So the bicarb leaves, the chloride comes in. Then you have that equation here. This is at the air sacs, at the lungs. Look at that equation and tell me how it relates to that equation.
Reverse.
It's the reverse. So at my lungs, I'm going to reverse my equation. Write it again. Here we go. HCO3 minus plus H plus makes H2CO3, which makes H2O plus CO2. All right? I'm going to reverse my equation. Well, where did this HCO3 come from? That went into the RBC. And therefore, what had to come out of the RBC to do this?
Chloride.
The chloride had to leave. I'm just reversing what I did. So when I put it together, I took a bicarb out and a chlorine in. Over here, I have to put the chlorine out and the bicarb in. And then that drives the equation this way. And the CO2 is going to go out of my lungs using carbonic anhydrase. So let's watch that some more as you're staring at me with those evil eyes. Right. I'm going to go back through both those again, okay?
A slightly larger percent of the carbon dioxide is transported bound to hemoglobin as carbaminohemoglobin. Carbaminohemoglobin is formed near metabolically active cells and carries carbon dioxide
number 2.
from. Most of the
This
carbon
one.
dioxide is
Number 3.
carried in the form of bicarbonate ions in the plasma. The carbon dioxide in the plasma diffuses into the red blood cell. There it undergoes a chemical reaction catalyzed by the enzyme carbonic anhydrase and is rapidly converted to bicarbonate ions.
There's the equation.
As
number
levels
3.
of carbon dioxide increase, the production of bicarbonate ions increases. The bicarbonate ion diffuses into the plasma, where it is carried to the lungs.
Okay.
In order to maintain electrical balance in the red blood cell, the movement of the negatively charged bicarbonate ions out of the cell is balanced with the movement of negatively charged chloride ions into the cell. This process is called the chloride shift. Carbon dioxide is generated near the alveoli.
Look here, I'm reversing it. So now the bicarb goes in, the chlorine should come out. I drive the equation the opposite direction. I'm going to let the CO2 come out of my RBCs to go to my lungs, which is reversing my equation.
Carbon dioxide that is produced diffuses into the alveolus for removal from the body.
So again, each equation is the opposite one. Okay. So to help you maybe with that concept, because thou shalt know these reactions thou shalt. You have to memorize them. I'm going to show you a picture here that may help you, maybe not. Right, I'm going to do an easy picture first. We're going to walk through all the equations, all four columns and rows here. Right, the 2 oxygens and the 2 carbon dioxides. So here's my air sac. We're going to do the oxygen first. So oxygen, take a deep breath. Oxygen diffuses into my blood. Here's my blood cell. I'm loading. So the Hb plus O2 makes HbO2, oxyhemoglobin. My heart pumps it to my body, blah. I then reverse my equation. I unload, dissociate into my tissues, right? That's the oxygen 2. The tissues convert that into energy, making CO2. CO2 then goes into my blood. The most common one is this one, where I make bicarbonate ions and carbonic acid. It then gets sent to my lungs. I undo that to get rid of it, right? Now, the more official looking picture, the one you actually want to take a picture of with your phone, is this one here. This shows all of the carbon dioxide mechanisms in one slide. So go for that one. Is it okay in the dark?
Yeah.
All right. Now I'll walk you through this in a second. Okay? Let's walk through it. All right? So over here, minor player, the CO2 just gets bubbled into your blood. That's like soda pop at my body. It sends my lungs and it reverses. It goes out of my blood. Here's that carbaminohemoglobin thing. So it comes out of my tissues, binds to the hemoglobin in a separate binding site, gets carried to the lungs, and you unbind it and it sends off. The one that you have to spend your life memorizing is this one. So CO2 comes out of my tissues, enters an RBC, gets converted by carbonic anhydrase through all this stuff to make bicarbonate, hydrogen ions, and carbonic acid. That gets spit out, which the chlorine would come in to replace it. If I go to my lungs, I reverse all this to put the CO2 back out. So those are the 3 mechanisms of carbon transport. Question? Yes, Bill.
So the bicarbonate ion leaves the cell
Yes.
and then re-enters it?
Yes.
Why doesn't it just stay?
I didn't build you that way.
Okay.
So I don't know. It's just the way your body does it, is it goes out, travels in the plasma, and then goes back in. Just the way your cells do it.
Sounds really pointless.
It does seem pointless, but I didn't build it. So one argument is the carbonic anhydrase is only in the cell. So if you just left it outside, you'd never convert it back. So that enzyme is what's essential to do that. So the enzyme's in the cell. Oh, I don't know. The enzyme doesn't have to be in the cell. So it's just the way it is. Come back. You okay? So thou shalt memorize which equation is where, is loading or unloading, and what it does. All right?
So
Yes.
carbonic acid is unstable. It just doesn't want to stay like that. That's why. it
More or less.
progresses to
It
the-
has an equilibrium, so you always have all 3 at all times because they balance. Yeah, you can change one and it causes the other ones to change. Okay, so now we're going to make the big jump in logic here. Okay. Guys. All right, we're going to make a graph.
Our favorite.
And at some point, you're going to say April Fools, right?
Never. Yeah, this class was just a joke. now. I'm graphing blood acidity over time, or blood acidity per unit time. All right, so this takes a little bit of some chemistry thinking here, okay? So based upon what you know from today only, can anyone find an equation up there that somehow influences acidity? Look over there somewhere. Which equation by number over here would have an influence on acid?
3.
Number 3, so you look here. I make acid in this equation, right? It's produced. So, if my blood is getting more acidic, the acidity is going up, the brain perceives that equation 3 is causing it. Right? And what's causing that acid to be formed over there? Where's it coming from? What's making it? Was it? From CO2. CO2 from my tissues makes this appear. So your brain thinks that blood acidity is due to CO2 levels in the RBC, basically. Because the CO2 is what makes the RBC become more or less acidic. Does that make sense? So if my body is getting more acidic, the brain thinks it's because equation 3 is happening more. So what could my brain do if there's more acidity than it wants? How could it deal with this? Where could you send all that acid to get rid of it? To my lungs. Because if I send it to my lungs, I'll have this equation 3. I take the acid away by breathing out, right? So what will my brain do when the graph goes up? You're going to exhale more. Your brain is going to order you to exhale more. Because what do you exhale? So that's going to remove the CO2 from my body via equation 3 on the left and purge the acid out. It's going to lower the acidity. All right, let's do that. All right. So now, let's pretend that you don't have a lot of acidity in your blood. Tell me what a brain might want to do about that.
Not breathe.
Not breathe. I'm going to exhale less. Because if I don't exhale, I'm not removing the CO2. Therefore, it stays equation 3 on the right, and the acid levels climb back up. But you realize you can't just exhale, right? Try that sometime. Just keep exhaling. So what do you do instead of exhaling more? What does your brain order you to do? You have to breathe more. So you breathe more often. You breathe faster. Because you can't just exhale, so you got to inhale too. So you breathe faster to remove the acidity. So instead of exhaling less, the only thing you can do is what? Breathe slower. And that would change the amount of CO2 in equation 3 to affect acidity. So EMTs routinely learn that the reason you exhale is to blow off acid. Sounds obscene, but it works. You're breathing to blow the acid out of your body by equation 3 on the left. Right? If you exhale less, it's to retain acid in the body. Because the acid comes from the CO2. Does that make sense? So on your quiz and exam, you're never going to write down, do you breathe to get oxygen in? That is wrong. Why do you breathe? To get the acid out. That's the answer for normal people. You breathe to get the acids in or out of your body. Yes?
I was curious why the numbers, the concentration
Yes.
of oxygen was so much, there was such a greater difference for oxygen than for CO2?
Because your brain's much more sensitive to CO2. So every 1
Okay.
unit of CO2 will change the breathing rate. It takes 50 units of oxygen to see a similar rate. So the brain doesn't even notice oxygen's missing. All it cares about is the acid level. It's much more sensitive. All right? To prove that I'm not making this up much, all right? I'm going to show you something from last term. Anyone remember what these things are? It says up there. Dual and pons. What does this have to do with lungs? That's so last term.
Regulation of breathing.
All right. Remember that was the breathing regulation, breathing mechanics stuff. Okay, so you have your pons and medulla. Remember medulla did the math, and the pons told you faster or slower. So